Hello friends, today's question. A block of mass m lying on a smooth horizontal surface is attached to the spring of negligible mass of spring constant k. The other end of the spring is fixed as shown in the figure. The block is initially at rest in its equilibrium position. If now the block is pulled with a constant force F, the maximum speed of the block is, so this is block m, force is being applied, and this is spring which is having a constant of k. Force constant is, spring constant is k. And we have to find out the maximum speed of the block. So before, in this question rather, we can say that the conservation of energy principle is going to be applied. And before going to the solution of the question, let me give a brief idea or brief, you can say, introduction how the energy behaves when the spring is under a force and the mass is attached to the spring. So this can be explained basically using figure. So let us draw a figure, and we start by using that this is a fixed portion of the wall, and we have spring which is stretched from its mean position. So this is a mass m, and we are going to apply a force F. In this direction is being applied, and this is the extreme position, and somewhere here this is our mean position. Okay, so at extreme position we say, let us suppose the displacement is maximum amplitude, that is equal to plus a, and at this point the velocity will be equal to 0. So if velocity is equal to 0, then from here we can say that the kinetic energy will be equal to 0. And this is the mean position. Let us suppose that is represented as x is equal to 0. So we can write in this that at this particular moment the entire energy will be stored in the spring. Okay. So we can say that all the energy is stored in the spring and which is given as U is equal to half k a square, and as velocity is 0, so we can say its kinetic energy will be equal to 0 because velocity at this point is 0. Okay, and this is when you can say mass m is at extreme position, that is x is equal to plus a. Now for the second case, the spring is going to have a tendency to come back to its mean position. So let me draw the mean position here. So at this position, this is our mean position. So now the mass will be at this point, and at this point the spring is neither compressed nor it is extended or stretched, and this was our x is equal to plus a, and now the mass is at mean position, that x is equal to 0. Okay. So therefore we can say that at mean position, the spring is neither compressed, nor stretched. Therefore the potential energy of the spring will be equal to 0. Therefore, potential energy of the spring will be equal to 0. So it means the total energy will be now equal to kinetic energy. So you can say that total energy will be equal to kinetic energy, and that will be equal to half m, and at this point its velocity will be maximum, so this will be our minus v max and whole square. Now it is going to overshoot the mean position, and the spring will be traveling, or we can say mass will be traveling to the left side, and the spring will be compressed. Okay. Once again, let us draw the figure for the compressed. So this is our mean position x equal to 0, and this is our extreme position x is equal to plus a. Now the spring will be compressed so that it goes to the other side with the maximum compression, and this will be our x is equal to minus a. So now the spring is compressed. So now the mass is at minus a. So we can say mass moves to x is equal to minus a, and once again at this the velocity will be equal to 0, therefore the kinetic energy will be also equal to 0, and in this position velocity will be equal to v max. So at mass moves to x equal to a, and here velocity is equal to 0, therefore kinetic energy will be also equal to 0. So the energy stored by the spring, which is compressed, okay, now the energy will be stored in the form of compression. So therefore you can write that energy stored by the spring which is compressed, and this energy will be given as U is equal to half m, and we get U half k minus a whole square, and we can say that the total energy from the entire so we can say that the total energy of the system, total energy of the system here means block plus spring will be equal to half k a square, which is nothing but kinetic energy plus potential energy. So therefore we can write that our E total will be equal to U plus k, and that is equal to half k x square plus half m v square. And we can also plot the graph of the kinetic energy as well as potential energy. So let us say that if the position is given as x, which is equal to a cos of omega t plus phi. So therefore the velocity, which will be derivative of x, will be given as dx upon dt, which will be minus a omega, and we get this as sine of omega t plus 5. So we can plot the kinetic energy as well as, we can plot U as well as K with respect to time. Okay, so let's plot it. So this is our energy, and let us start by plotting first of all our U. U is equal to A cos omega t, and this is our 0. So U is going to start with our maximum, and it will be going like this, and this will be our T by 4, and this will be our T by 2, and we can also plot this as, let us complete one full, and we get this as like this, and this will be our 3T by 4, and this will be our T. Okay, so this is our U. Similarly, we can plot for K also, and we are going to get K like this, one second, yeah, it goes like this, like this, like this. Let me redraw it again. There was slight mistake on my part. So this is our energy, and this is our, so we are starting with U, and so this will be our T by 4, and we have this as T by 2, so this will be 3T by 4, and this will be our T. So this is graph for our U, and we start for now K, and this is our K. So this is our energy in terms of U and K, and the total energy will be represented by this. So this will be our E total, which is always constant. Okay, and let us plot the respective x and velocity, how it is going to vary. So we can say that our x so this is our distance x, and we have plus a minus a, so it will be going like this and like this, so this will be our x, and we can plot our velocity also. So this is our velocity, and x was our displacement. So velocity, we are going to get it as and this will be our velocity. Okay, it will be more of a symmetrical. Now we plotted energy, and this was our with respect to time, and this is our displacement as well as velocity. We can also plot the energy function with respect to position. Okay, energy as a function of position. Energy as a function of position, and this is quite, you can say, easy to plot. So this is your mean position, which is x equal to 0, and this is our energy, and this is our displacement x. So we get the graph will be our like this, and we have here minus of a, and this we have a plus of a, and we are going to have the horizontal line which will be our E total, and we are going to have other graph which will be just inverted of the previous one. So this is our U, and this is our K, and we get the horizontal which is constant. We have a E total. So this x naught is our equilibrium position, and this is our maximum position on one side, and this is also maximum position on the other side. And we can also say the direction of the force will be always towards the mean position. Okay, and we can find out the force from the slope of the graph. So we can say our force F will be equal to slope of the graph, and the formula will be equal to F is equal to minus du by dx. And here x naught is also called as a equilibrium position, or we can say, sorry, x equal to 0 is called as a equilibrium position, or it is also called as a stable equilibrium position. So we can write that x is equal to 0, it is called as a stable equilibrium position. Now there is a, you can say, there is a stable equilibrium position. So accordingly there is an unstable equilibrium position, and also there is a half stable equilibrium position. So let us clarify those concepts also. So let us find out what is the actual meaning of stable equilibrium position. So we can say, if the equilibrium point is stable, if the equilibrium point is stable, a slight disturbance of the object if the equilibrium point is stable, a slight disturbance of an object that is initially at stable equilibrium of an object that is initially at stable equilibrium will cause the object to oscillate around that point. Will cause the object to oscillate around that point. Around that point. Okay. So here that point means that in case of the spring, and we already said this is our mean position. So in stable equilibrium, the object, if it disturbed slightly from this mean position, is going to oscillate about this point. So the point is nothing but the mean position point about which it is going to oscillate. So from here we can also draw another conclusion that the stable point occurs because the forces on either side are pointing towards the stable point. Because the forces on either side are directed towards it. So you can see from this figure also, this is our equilibrium stable point, and forces are directed towards the stable point. And this is also true in case of the spring also. The spring is going to exert a force toward the stable point when it is extended, and when it is compressed, it is also once again going to exert a force toward this mean position, that is a stable point. And let's now understand what's the meaning of unstable equilibrium. So we can say for unstable equilibrium, for a slight disturbance object do not return to its equilibrium point. Object do not return to equilibrium point. Or we can also call that as a mean position. It does not return back to its mean position. Okay. So we can represent, or we can see draw with the help of a figure also. What does it mean? So if you have a surface which is something like this, and this is the mean position, and this is the object. So every time we give it a slight disturbance towards the left or right, there will be the forces which will be always acting towards the mean position in this direction. Okay, so it is going to, you can say, vibrate or move about this mean position, and the forces will be acting towards the mean position. So this is our stable equilibrium. And let us, now this is our object, and we have a mean position, and in case we give a slight disturbance to it, so it is going to move in this either direction, and the forces which will be acting will be in the opposite direction. So this is our force acting on the object. So this is our unstable equilibrium, and there is a half stable, and which can be drawn something like this. So we have an object, and in this direction, so the forces will be acting in this direction and in this direction. Okay, so we call this as a half stable. Half stable. It is called half stable because one of the force is pointing towards the mean position. Okay, here both the forces are not towards the mean position, and here both the forces are towards the mean position. So this is stable, unstable, and this is half stable. And half stable, we can say one force is pointing toward the fixed point. One force rather we can say points toward the fixed position, towards the fixed position. And we can also represent this with the help of the figure also, graphical representation also. So we have F, and here also F, and this is a fixed position. So the forces will be pointing towards the fixed position, and this is our displacement. So we can see F, which is equal to minus dx, which is du by dx, is in this case also greater than 0. And here also F is equal to minus du by dx will be also greater than 0, because the direction of the force as well as x displacement is always in the opposite direction. And for unstable, or we can say for half stable, we can draw it like this. So this is our energy U, and we have x, and this is our mean position. So the forces F will be acting in only one direction, both the forces. So we can say this is our fixed position. So we are going to F here and here, they are both acting towards one direction, and one of the force will be pointing towards the fixed position. So we can write here that F will be equal to minus, once again, du by dx, and that will be equal to less than 0. And here also F will be equal to minus du by dx, and that will be also less than 0. So this is the basic idea about the forces which will be acting on the, you can say, object. Now let us solve the question which was our basic. So in the question, we were supposed to find out what will be the maximum velocity in this case. So let me redraw the figure. So we are given that the spring is first is at a mean position, and then it is extended with the application of the force. So this is a mean position given at x equals 0, and the spring is extended. So this is our m, and this is our x is equal to x maximum. So therefore we can say that on the application of force F, on the application of force F, if X max is the maximum extension, if X max is the maximum extension, then if X max is the maximum extension, so therefore we can say at this point, at X is equal to X max, at this position, the block will be in equilibrium. The block will be in equilibrium, so which basically means the applied force will be equal to restoring force. Applied force will be equal to restoring force, or we can say F is equal to Fs, that is restoring force because of the spring, and that will equal to K X max. So from here we can find out that our X max will be equal to F upon K. And at this particular point, the energy stored in the spring, at this point, which means when X is equal to X max, the energy stored in the spring, in the spring, which is given as U max, will be equal to half K X max whole square. And we are supposed to find out the maximum velocity. So we can say for maximum velocity, the kinetic energy will be also maximum. For maximum speed, the kinetic energy should also be maximum. So we can write that our kinetic energy maximum will be equal to half mv square max. And now we are going to use conservation of energy. Using conservation of energy, U max should be equal to kinetic energy max. U max is given as half K X square max is equal to half m v square max. Half goes with half, so from here we can write that v square max will be equal to K upon m, and we have here x square max. But we just found out that x square max is equal to F upon K. So we substitute it here and we get this as V square max will be equal to K upon M multiplied by F upon K whole square. So this becomes K M F square K square. K square cancel with K, and this is equal to F square upon MK. So we get maximum velocity Vmax is equal to F upon square root of M times K, and this is our maximum speed of the block. And the option that is correct one is given as B. So B option is the correct one. Okay. We can say this is the maximum speed, and option B is correct. So this question was quite simple. Only we need the basic understanding how the energy conservation takes place when the spring is stretched. Okay. So this finally completes the question. Thank you.